Hi everybody, this is Dr. Bricker here with some hints for homework number 10, which covers Chapter 13. Chapter 13 is about fluids, both fluid statics and fluid dynamics. So let's take a look at this. First problem, we have a 68 kilogram college student. Density is given, 1,050 kilograms per cubic meter. What is the volume? So you probably have seen this kind of problem going back all the way to like 6th grade or something like that, but let me just refresh your memory about this. Okay, so density is mass divided by volume. So we're trying to figure out the volume in this problem, so a little bit of algebra. Volume then would be mass divided by density. And if you notice, I use this big V for volume instead of little v. We'll do some problems in this chapter which involve volume and velocity, and it can become really confusing. So this symbol, it's not P, it's rho. We also have pressure in this chapter, so don't write P for this. You might get confused. So rho, mass over volume, kilograms per cubic meter. That's the SI unit. So in this problem, you're given the mass and you're given the density. You'll see that the volume will come out in kilograms cubed. All right, let's look at the next one. Okay, so fat cells in humans are composed almost entirely of pure triglycerides with an average density of about 900 kilograms per cubic meter, so less than water. If 20% of the mass of a 70 kilogram student's body is fat, what is the total volume of fat? Okay, so without putting any numbers in it, 20% of 70, so that would be 14. 10% of 70 would be 7, so this is 20%, making it 14. So we've got 14 kilograms of fat. We know the density of fat here. So if you know the density and you know the mass, you can figure out the volume. Really similar to the previous problem. Okay, moving right along to the next one. The deepest point in the ocean is 11 kilometers below sea level. Deeper than Mount Everest is tall. What is the pressure at this depth? So with pressure, you've got to be careful. They want the answer in atmospheres. So if you imagine you go deeper and deeper into the ocean, the pressure gets larger and larger because of all that volume above you. So let's actually calculate this pressure. Okay, so here's the top of the ocean. This is just atmospheric pressure. So atmospheric pressure, 1.01 times 10 to the 5th newtons per square meter, or you could say 1.01 times 10 to the 5th pascals. A newton per square meter is a pascal. So that's 1 atmosphere. Okay, and then we want to figure out the pressure here at this depth. And the depth here is 11 kilometers, so 11 times 10 to the 3rd. So what are we going to use for the density of water? It's an ocean, so I'm going to use the density of salt water. And this is in a table in the chapter. So the the pressure at depth is the pressure at the top plus rho times g times y. So you know this, we're assuming this is atmospheric pressure, 1.01 times 10 to the 5th. And then we have rho, which we know because it's seawater, times g times y. So let me do one more step here. When you put this all together, we have all the information here. Pascals, 1,030 kilograms per cubic meter times 9.8. I'm running out of room. Meters per second squared. And then times 11 times 10 to the 3rd meters. You'll get this answer, and it will be in pascals. If you notice, this part will come out in newtons per square meter, kilogram meter per second squared, and then per square meter. This will come out in pascals. And then you'll have to turn it into atmospheres, and here's the conversion factor. 1 atmosphere, 1.013 times 10 to the 5th pascals. Okay, let's look at the next one. Okay, so we have a container of gas here. This is mercury, and this is open to the atmosphere. and we want to know what is the gas pressure inside the box that's shown. We've got a few different dimensions here. So now you have to imagine if the pressure of the gas was greater, that would push the mercury this way. So the atmospheric pressure is open here. The atmosphere is pushing mercury this way. Gas pressure is pushing mercury that way. Atmospheric pressure is actually winning, right? Because this is pushed down farther. This level here is lower than this level here. So the pressure of the gas is going to be less than atmospheric pressure. If the pressure of the gas were more, this is the other way of looking at it, this would push mercury this way. And that's not what's going on. One thing that we do know is the pressure at this level is the same as the pressure at this level. Okay, so when you have a fluid like this, like mercury, and you have a height here and a height here, the pressures have to be the same. If they weren't the same at this same height, then the fluid actually would be moving, and it's not. Okay, so let's sketch this out and solve this problem. This is something called a manometer. Okay, so here's the picture we have. A few different dimensions were given. This was 6 centimeters. This whole thing was 16 centimeters. So now I know that this must be 10, right? From this point up to here, because this is 10, we have another 6. I know that the pressure at this point is just atmospheric pressure. So why don't I just call this one like P1 or something. It's open to the atmosphere. That's 1.01 times 10 to the third pascals. And then this is at the same level, so I know it's got to be the same pressure. This pressure is also 1.01 times 10 to the third, or 10 to the fifth. I think I said third, but I meant fifth. 1.01 times 10 to the fifth. 1.01 times 10 to the fifth pascals. So I know that this pressure, I called it P1 over there, I'll just call it P1 over here. The pressure here is equal to the pressure here plus rho GH of this column. So let me write out what I've just said. P1, pressure at depth, is equal to the pressure at the top, that's the gas pressure, plus rho GY of this column. Just like we did with the ocean problem, the pressure at the bottom of the ocean was due to the pressure at the top of the ocean plus rho GY. It's the same thing here. The pressure here at depth is equal to the pressure at the top plus rho GY. This is the Y I'm talking about, the 10 centimeters. So rho GY. You have to do a little bit of algebra to solve for the gas pressure, but you can do that. You know this. It's mercury. Look it up in the book. I've already done that for you, actually. 13,600. G is 9.8. Y is 10 centimeters. Just be careful. Put that into meters, right? So 10 centimeters, there's 100 centimeters per meter. Okay, so a little bit of algebra solve for the gas pressure. All right, moving on to the next one. Okay, so we have hippos spend most of their lives in water, but amazingly they don't swim. They have, like manatees, very little body fat. The density of a hippo's body is 1,030. So actually the density is greater than fresh water and similar to salt water. So it sinks to the bottom of a freshwater lake. Okay, so the density of the hippo is 1,030. Density of water is 1,000. So more dense, sinks to the bottom. So it sinks to the bottom of a freshwater lake, lakes and rivers it frequents, and then simply walks along the bottom. So the hippo feels lighter because you've got a buoyant force pushing up and weight pulling down. So the buoyant force helps out. A lot of these problems with the buoyant force are similar to what we did in chapter 4 and 5. It's just now we have a new force we can play around with, something called the buoyant force. Okay, and there's a picture of a hippo running around at the bottom. So here's the density of the hippo. We've got a 1,500 kilogram hippo is completely submerged, standing on the bottom of the lake. What is the approximate value of the upward normal force on the hippo? Okay, so if the hippo were not in water, the normal force up would be equal to the weight that's down. The difference with this problem is now we have this additional force up, something called the buoyant force that we can play around with. So taking into account that we have the buoyant force, how much would the normal force have to be? So we'll need a free body diagram. All right, let's take a look at that. Okay, so as far as the free body diagram goes, we have the weight of the hippo, that's this way, and that's equal to mg. Upward, we've got the normal force, but we also have this new force called the buoyant force, so both of those are up. That allows the normal force to be less than it would be if we're just in air. So we've got buoyant force up plus the normal force up is equal to the weight. Okay, so the buoyant force, that's the new thing from this chapter. This is the density of the fluid, volume of the fluid that is displaced, and times g. So let me say this again. So the buoyant force is the density of the fluid, and we're just in water, so the density of the fluid is 1,000. The volume of the fluid that's displaced. So when the hippo is completely underwater, the volume of the fluid that's displaced is the same thing as the volume of the hippo. So if you put something and it's completely submerged, say you put a baseball, and you know the volume of a baseball, you put it into a beaker, the volume displaced, in other words, the volume that goes up in the beaker would be the same as the volume of the ball that you put into it. So in this example, the hippo is completely submerged, so the volume of the hippo is the same thing as the volume that's displaced. Now if you took an object and you only submerged it halfway in a fluid, then you would just use half of the volume of the object, because the volume of the fluid displaced would just be half as much. Okay, so this is the new part here. This is old. Free body diagrams, balancing forces. This is new, this new force that we've had called the buoyant force. Okay, so weight is mg. We're given the mass and we know what g is. This is what we're trying to figure out. Let me just do one more step of algebra before we move on. Normal force, weight minus buoyant force. So the weight would be mg. The buoyant force would be the volume of the fluid. Density of the fluid, volume of the fluid. So how are you going to get the volume of the fluid? Well, the volume of the fluid is the same thing as the volume of the hippo, because it's completely submerged. So you have to do a little bit of algebra to do that. So we'll get the volume of the hippo. You can do that, though, because you know the density of the hippo and you know the mass of the hippo. So figure out the volume of the hippo, and then times g. Okay, and then you'll see the normal force. Obviously, it's got to be less than mg. Now, if you're not submerged, this part goes away, and then the normal force is just equal to mg. But here you've got this additional force helping you out, the buoyant force. Okay, let's look at the next one. Okay, so this one actually has a video tutor solution. You can take a look at that. The author of the book can help you out. Remember, you can hit review here and go right to the exact section of the book that pertains to this sort of problem. So here we have a block of aluminum. Density of aluminum is given. The volume of the aluminum is given. Completely submerged in ethyl alcohol. And then we want to know what is the tension in the string. So if you imagine, the tension in the string would be less than it normally is. By normally, I mean if it was just hanging in air, there would be a certain amount of tension. But here, you have the buoyant force helping out. So let me just kind of sketch out the free body diagram for this one. Alright, so similar to the hippo problem, actually. It's just instead of there being a normal force up, we have tension that's up. That's the free body diagram. So we know that the tension plus the buoyant force has to be equal to the weight, to mg. So then the tension is mg minus the buoyant force. So you can see it's really similar to what we did before. Now the buoyant force is going to be the density of the fluid. You'll have to look up ethyl alcohol in the book. The volume of the fluid that's displaced, well, that turns out to be the same thing as the volume of the object again, the aluminum, and then times g, right? Because it's completely submerged. This and this are the same thing. Okay, they don't actually give you the mass of aluminum directly, but they give you the density and the volume, so you can figure out the mass. One thing to be careful of is 100 cubic centimeters. That's not an SI unit. we want to turn that into cubic meters. Be careful, you don't just divide or multiply by 100. You have to look at it like this. 1 cubic meter would be 100 centimeters times 100 centimeters times 100 centimeters. So to put 100 cubic centimeters into cubic meters, you actually have to divide by 3 times, right? Because 1 cubic meter is 100 times 100 times 100 cubic centimeters. Okay, but then you have all the information after that to figure out the tension. All right, let's look at the next one. Okay, so the first part of the chapter, and really the first 6 questions, dealt with fluid statics, fluids not moving. The last 4 questions deal with fluid dynamics. So as far as chapter 13 goes, I didn't do anything with turbulent flow, so everything is a nice streamline flow. You'll see that there's a little bit at the end of the chapter about viscosity and things like that, but I didn't include viscosity. I went with the very general laminar fluid flow. So don't worry about viscosity. Viscosity is basically friction when water moves, like something like molasses would have a viscous force. We're not worried about that. We're worried about nice clean flow, not turbulent flow. So we go through the Bernoulli's force section, but after that we stop. Okay, so let's look at what we have here. Your low flow shower head is delivering 1 times 10 to the minus 4 cubic meters per second. So that's how many volumes per second. That's about 1.6 gallons per minute, just as a reference. If this is the only water being used in your house, how fast is the water moving through your house's water supply line, which has a diameter of about 3/4 of an inch, or 0.021 meters? Okay, so given this volume flow rate, how fast is the water going through a typical pipe? Okay, so let's look at volume flow rate. Okay, so here's a piece of pipe. Here's the cross-sectional area of one side, so it's kind of like a cylinder. Water's flowing through here. So here's the area, here's some dimension x. If I wanted to figure out the volume here would be the area times x. If I want to know the volume per time, I could just divide both sides by the time. So this is the volume flow rate. It's called Q here. So volume flow rate is Q, volume per time. And then area, and then x over t is the velocity. So if you're wondering why volume flow rate is area times velocity, you have to think of the velocity as being this distance, and then divide the whole thing by time. The part that's changing is the x part. So we could identify that as x over t as the velocity. So this is why this is little v for velocity, this is big V for volume. It can be confusing, so you have to keep track of those things. Okay, good. So in this problem, I believe that they gave us the volume flow rate, and we want to figure out the velocity. How much is the velocity? They don't give us the area directly, but we have to assume the pipe has this kind of a shape. So you can figure out the area. Pi r squared or pi d squared over 4. So volume flow rate's given. You'll have to do a little bit of work to get the, volume flow rate's given, do a little bit of work to get the area, and then solve for the velocity. Okay, let's look at the next one. Okay, so in this one we have a 1 centimeter diameter pipe, widens to 2 centimeters, then narrows to a 1/2 centimeter. Liquid flows through the first part at 4 meters per second. What is the speed in the second part? What is the speed in the third part? Okay, so the thing to think about this is something called the continuity condition, continuity equation. The volume that's coming out of the pipe cannot change. Whether it gets thinner or thicker, it's the same volume that's coming out. Now when you take the pipe and you scrunch it down and make the area smaller, like if you had a hose and you put your thumb over the end, it's the same amount of water that comes out, but if you put your thumb over the end, you make the area smaller, so you make the speed greater. So you might think it's directly proportional to the size, but it's not. So let me show you why it's not, and we can solve this problem. Okay, so here's the pipe. We've got 1 centimeter, and we know it's going at 4 meters per second. Now the pipe gets twice as big, up to 2 centimeters. So you might think that the speed is just cut in half, but it's not. and you'll see why in a minute. And then here it goes from 1 all the way up to 2, but then back down to 0.5. And we want to know the speed here and the speed here. Again, the thing that's not going to change is the volume flow rate. The Q is the same. It's the same amount of volume per time. Same amount of cubic meters per second. So the way I could do this, I'll just call this one V1. V1 times area 1, it's got to be equal to V2 times area 2, that's V3 times area 3. Because the volume flow rate doesn't change. Now, remember the area, let me take another step here. This would be pi diameter 1 squared over 4. This would be V2, and then the area would be pi diameter 2 squared divided by 4. Remember, it's the area of a circle. This would be V3 pi d3 squared over 4. The pi's and the 4's all cancel out. So I've got this situation where I've got V1 diameter 1 squared. That's got to be equal to V2 diameter 2 squared. That's equal to V3 diameter 3 squared. Okay, so you know all the different diameters, 1, 2, and 3. So if you wanted to get V2, you could use this part of the equation. You know V1, you know D1, D2. The only thing that you wouldn't know is V2, so you can do that to solve for V2. Same idea here. You know this and this have to be equal to each other. The only thing that you don't know is what you're looking for. Or if you want to look at it like this, this is squared and this is squared. So if this is twice as big, because of the relationship between D1 and D2, that it's squared, if this diameter is twice as big, the speed's got to be 1/4 as much for the equality to hold true. Same thing over here. If I'm comparing V1 and V3, if the diameter is half as much, when I square it, that means that the speed's going to be 4 times as much. So if I had 16 here, sorry, thinking ahead already. If I've got 4 here and I cut the diameter in half, this has to be 4 times greater, so this would have to be 16 there. So you could do it the first way I said, more mathematically rigorous. Just take this equation, this and this and this, you can solve for V2. Or for the part B, this and this and this, you can solve for V3. Or you could realize the relationship between, the way that it goes, that D1 squared and D2 squared. So making it twice as big makes the speed 1/4 as much. Okay, so that was a volume flow rate problem. Let's take a look at the next one. Okay, so during typical urination, a man releases 400 milliliters of urine. Okay, that's a perfectly good unit. It's just not an SI unit, so you'll have to turn that into cubic meters. It'll be a really, really small amount of cubic meters in 30 seconds. So that's really the volume flow rate, 400 milliliters in 30 seconds, but just make sure that you put that into SI units, convert milliliters into cubic meters. You'll have to look up the conversion factor. Here's a nice place to start this review section here. Okay, which can be modeled as a tube 4 millimeters in diameter and 20 centimeters long. Assume that the urine has the same density of water, so 1,000 kilograms per cubic meter, and the viscosity can be ignored. Okay, so no sort of friction associated with the fluid. What is the flow speed in the urethra? So what's the flow speed in this tube? And then part B, if we assume that the fluid is released at the same height as the bladder and that the fluid is at rest in the bladder, which is a reasonable assumption, what gauge pressure in the bladder could produce this flow? Okay, and the gauge pressure is the difference between the bladder pressure and atmospheric pressure. Okay, so it's a volume flow rate problem. In addition to that, it's a Bernoulli's equation problem. Good, so let's take a look at that. Okay, so we've got 400 milliliters in 30 seconds. I looked up the conversion factor. 1 milliliter is 1 to the minus 6 cubic meters. So you could figure out the volume flow rate from this. Put that into cubic meters, 30 seconds. You can figure out the volume flow rate. And then you know the volume flow rate from what we were just talking about. It's area times velocity. So the velocity then, like we've done before, volume flow rate, which you'll have to do some work to get, divided by the cross-sectional area. Same thing like before. Pi d squared over 4, or if you want, pi r squared. They give you the diameter, so I just left it in terms of the diameter. So then you can get the volume flow rate, no problem. Similar to what we've done before, it's just you have to do more work for Q, you've got to do more work for the area again. But then you can get the speed here. The second part is, what is the bladder pressure minus the atmospheric pressure? So we're going to assume that this is a tube and it's horizontal. So here you've got the pressure of the bladder, and they tell you that the fluid starts at rest. So initially there's no speed. Here, this is open to the atmosphere, and then this is the speed that you found in the first part. So this speed is what you found in the first part. So you go from nothing to something, there has to be a difference in pressure. The pressure here has to be bigger than the pressure here. Okay, so let's actually use Bernoulli's equation to solve this. Okay, so you got to look at what's going on here and look at what's going on here. So it's a horizontal tube, there's no change in height, so we don't have to worry about that part of Bernoulli's equation. But we have pressure at the bladder plus 1/2 the density of the fluid, velocity of the bladder squared, that's the kinetic energy term. So pressure, this would be the kinetic energy term. There would also be gravitational sort of potential energy term, but it's the same here and here, so we don't have to include that. So this is what's going on here. This would be equal to pressure atmosphere plus 1/2 rho v squared. And this is the v again that you figured out in the first part. And we're trying to figure out the difference between bladder pressure and atmospheric pressure. So we don't have to figure out this and this independently. We just want to know the difference. Bladder pressure minus atmospheric pressure. That's what they're asking about. So I'm subtracting this from both sides. That would be equal to 1/2 rho v squared minus 1/2 rho v bladder squared. And actually they tell you that this starts from rest. So that term goes away. So after all that, the bladder pressure minus atmospheric pressure turns out to be 1/2 rho v squared. And again, they say model this as being water, and the v comes from the first part. It's actually more complicated than this. It's not completely just reliant on differences in pressure. There's more going on physically, but this is a good place to start to figure out that difference in pressure. Alright, let's look at the final question. Now you see with this problem in the picture, this actually has a difference in height. The previous picture, it was just a horizontal tube, but here we've got like a kinetic energy type term. Here we have a, because there's some height here, we've got a gravitational potential energy sort of term. And we want to know what is the pressure up here. Now the volume flow rate equation still works. So if you have, if you know the volume flow rate here, it's the same as the volume flow rate here. Fluid is just coming out faster at the top because it's more constricted. And then be careful, we want the answer in kilopascals. Okay, so not a lot of information given here. You've got to rely on the picture to figure out how fast things are going. Okay, so let's put this on paper. Okay, so here's the picture. So keep the picture in mind again when I show you these numbers. So with Bernoulli's equation, we've got P1 plus 1/2 rho V1 squared plus rho GY1. That's the beginning of the pipe. That's got to be equal to P2, the pressure up there, plus 1/2 rho V2 squared plus rho GY2. There's a lot of parts to this, but you just have to keep track of them. It's not that it's hard to do that. It's just cumbersome, maybe. So y1 was 0. This term actually goes away. And then the only thing that you do not know is what you're looking for, which is P2. This is what you're looking for. You want it in kilopascals. So let me just do one more step. P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared. That's what V2's got to be equal to. Oh, I think I skipped one. Minus rho GY2 is equal to P2. Okay, make sure I did this right. P1, so pressure 1, 1/2 rho V1 squared. Okay, that's good. That term is 0. And then subtract this from both sides, 1/2 rho V2 squared, subtract rho GY2, and that gives you P2. So you have everything. Just make sure that you put this as 200 times 10 to the third pascals when you add it to all these other SI terms. And then you've got to convert the final answer. So ... get the final answer. It'll be in pascals. Convert it to kilopascals. Okay, then we move on to Chapter 12. So there's 6 questions from Chapter 12 on Homework 10. So Chapter 12 is the thermodynamics chapter. Some of the stuff you might have seen from chemistry, things like moles, Avogadro's number, the ideal gas law. So you might have some familiarity with that. Let's take a look at this one, though. Which contains the most moles? 10 grams of H2 gas, 100 grams of carbon, or 500 grams of lead? And what might be helpful is this periodic table. We're going to need to know the molecular mass of each of these, so the periodic table will help us. So I just clicked on that. Now we're assuming that it's hydrogen gas, so the 1 here means that there's 1 gram per mole, but it's H2 gas, so we have 2 grams per mole. And you can look through here. I believe carbon was one of the other ones. If you know carbon, it's 12. As you see here. And then we can find, I think it was lead. So here's lead right over here. Good, so yeah, lead, 207.2 grams per mole. Okay, so we know how many grams of the sample we have. That's given in the problem. And we know how many grams per mole, so you can figure out how many moles of each and then figure out which one has the most. So let's take a look at, say, I'll just do carbon and I'll leave the other ones for you. Okay, so we're given 100 grams of carbon, and we know it's 12 grams per mole. I showed you how to get that from the periodic table. Actually, I think they just write MOL now instead of MOLE. When I was a kid, we had to write the whole thing out. Anyway, the number of moles, that's what N is the grams of the sample that you have. So 100 grams of carbon divided by 12 grams per mole. This will tell you the amount of moles we have. So 100 divided by 12. Oops, 100 divided by 12. So about 8.33 moles. And that's of carbon. So you have to do the same thing for lead and do the same thing for the H2 gas. Okay, let's look at the next one. Well, before we go on, though, it might be tempting to just say, wow, 500 grams of lead, that's got to be the one that has the most moles, but it doesn't necessarily. You'll have to calculate that, right, because you know how many grams there are per mole. Okay, don't want to say too much more about that. Let's look at the next one then. An ideal gas at 20 degrees Celsius consists of 2.2 times 10 to the 22nd atoms. 3.9 joules, that's what J is there, of thermal energy are removed from the gas. What is the new temperature in degrees Celsius? Okay, good. Let's take a look at it. Okay, so I've got here 20 degrees Celsius, perfectly good unit. We just need to put that into Kelvin. We're given 2.2 times 10 to the 22nd atoms. Okay, so that's what big N is, the amount of atoms. Now the change in thermal energy is actually negative 3.9 joules because it's been removed. Okay, and we want to know what's the final temperature. Okay, so here's the formula that we can use. The change in thermal energy, 3/2 N, number of particles, so that's given. Boltzmann's constant, so that's just the constant, 1.38 to the minus 23rd joules per Kelvin, and then times the change in temperature. We're given the initial temperature, We just need to figure out the final temperature. Okay, so we'll have to do a little bit of algebra to this formula. Now we're given everything really except for the final temperature, because remember this delta T is T final minus T initial. So T final minus T initial. Okay, so let me put a little bit more detail into this formula. The change in energy, okay, that's something that we actually know. Multiply both sides by 2, divide both sides by 3, and the number of particles, Boltzmann's constant, this is equal to the change in temperature, which is T final minus T initial. Okay, so then I could add T initial to both sides. So I'll have 2/3 change in energy, don't forget the N, Boltzmann's constant, and then plus T initial is equal to T final. Okay, so now if you've taken energy away, you would expect that the temperature went down. Temperature just really is a measure of how fast the particles are moving. So if you've removed energy, you've taken away some of the speed. That's a way of thinking about it. So if removing energy means that the temperature has to have gone down. Okay? Okay, so let's actually put some numbers in here. 2/3, and now negative 3.9 joules. So let's be really careful with the units here. Make sure we see how everything works out. 3.9 joules, that's how much energy has been removed. Now the number of particles, 2.2 times 10 to the 22nd. And then we've got Boltzmann's constant down here. 1.38 times 10 to the minus 23rd joules per Kelvin, so you see how the joules cancels out, plus the initial temperature. So remember, this is 20 degrees Celsius. You've got to add 273 to that to put it into Kelvin. Remember, that's the formula. Add 273 to Celsius to give you Kelvin. So that would give us 293 Kelvin. So plus 293 Kelvin, that'll give us the final temperature. Okay, good, and you can see that the final temperature is going to be less than the initial temperature. Let me see if I can find my calculator. Okay, so 2 times, put it here so you can see it, 2 times negative 3.9 divided by the whole quantity here, 3 times 2.2 to the 22nd times 1.38 the negative 23rd. Okay, so minus 8.56, and then I still have plus 293. So 284. Final temperature about 284.4 Kelvin. Now, Mastering Physics actually wants it in Celsius, so now you've got to subtract 273 from that. And we get final temperature in Celsius of 11.4. Okay. So here's the next one, sort of a biology type question. When you stifle a sneeze, you can damage delicate tissues because the pressure of air that is not allowed to escape may rise to 45 kilopascals. Okay, so a pascal, remember, is a Newton per square meter. So we've got 44 times 10 to the third pascals. If this extra pressure acts on the inside of your 8.4 millimeter diameter eardrum, what's the outward force? Okay, so remember, pressure is force per area. So we're given this pressure. Here's the size of the eardrum. Now we could assume that it's circular, so we can get the area of the eardrum. Then we should be able to figure out what this outward force would be, this additional force, because of this this pressure here. All right, let's take a look at it. Okay, so here's the pressure. Again, 45 times 10 to the third pascals. Pascals, Newton per square meter, SI unit, that's good. The diameter of the eardrum is 8.4 times 10 to the minus third meters. So if you want to do it as a radius, just cut that in half. 4.2 times 10 to the minus third meters. Why would I want to do that? I want to get the area. So we're assuming the eardrum is circular. the area would be pi r squared. So just be careful with the units. So really you have the area here. You have the pressure given in the problem. We want to figure out what force goes along with that. So pressure, force divided by area, multiply both sides by the area, here's the force. Okay, so you have the pressure, you have to figure out what the area is, and then you can get the force. Now, you don't have to explicitly figure out the area, you can just put in the formula for the area. Pressure pi r squared, that's the force. And that will come out in newtons. Remember, a Pascal is a newton per square meter. When you multiply it by this r squared here, there's the square meter, the meter squared cancels out, and you're left with newtons. Okay, good. Let's look at the next one. Okay, a college student is working on her physics homework in her dorm room. Her room contains a total of 6 times 10 to the 26th gas molecules. As she works, her body is converting chemical energy into thermal energy at the rate of 125 watts. So remember, a watt is a joule per second. So every second, we've got 125 joules being converted. Chemical energy into thermal energy. Okay? If her dorm room were an isolated system, and it says here dorm rooms can certainly feel like that, all of this thermal energy were transferred into air in the room. By how much would the temperature increase in 16 minutes? And use the ideal gas model. And then here we want the answer in Celsius. Okay, good. And again, I've said this throughout the semester, but you can hit this review button to see what section of the book this problem comes from. Okay, let's take a look at it. Okay, so here's the amount of particles we have. Here's the power. So this is how many joules per second, really. Remember, that's what a watt is, a joule per second. We want to know how much the temperature is going to increase if all of that energy went into making the air, whatever molecules they are, move quicker. And this is happening over 16 minutes. Okay, so the change in thermal energy, just like we did before, 3/2 the amount of particles, Boltzmann's constant, which I've written here, and then times the change in temperature. So that's what we're trying to figure out, the change in temperature. We don't know if it's going from a certain value to another certain value. We just want to know the change in temperature. Okay, so let me multiply both sides by 2, divide both sides by 3, and Boltzmann's constant. And then we can get the change in temperature. So delta T turns out to be 2, change in thermal energy, divided by 3, the amount of particles, and Boltzmann's constant. Now, some things in some subjects in Physics 220 you have more intuition for, like speed, meters per second, you know, even the units make sense, force, things like that you see in everyday life. This is more abstract, so it's really important, in my opinion, to keep the units, making sure everything works out. I mean, you can't come up with this kind of formula off the top of your head. You really have to rely on you know, making maybe a little formula sheet and knowing what the units all stand for too. Okay, so again, the amount of particles given, Boltzmann's constant given. How are we going to get the change in thermal energy? Well, we know the power. We have 125 watts, or 125 joules per second. And again, you might have different numbers for this one. And we know the amount of time, 16 minutes. Okay, and then we know 1 minute, 60 seconds. This is the change in thermal energy. That's how much we're assuming all that energy goes into speeding up the particles. So this is the change in thermal energy. So 125 joules per second. You can see the seconds cancel out, the minutes cancel out, and then you're just left with the change in thermal energy here. So you'll need this to go in here, and then you have everything, and you'll have the change in thermal. Put everything in, you'll have the change in temperature. This will come out automatically in Kelvin, or yeah, Kelvin. I think that's what they actually want the number in. Okay, let's look at the next one. Actually, they want the answer in Celsius. The answer that you get by putting numbers in will be in Kelvin. Remember to change it to Celsius. Celsius plus 273 gives you Kelvin, so you'll have to take that into account and put it into degrees Celsius then. Okay, so Celsius and Kelvin are related by that 273 number. Okay. Okay, here's the next one. Suppose you start your day in Denver on a cool 10 degrees Celsius spring day. The local atmospheric pressure is 85 kilopascals. You fill your car's tire until the gauge pressure reads 210 kilopascals, which is about 30 psi. You then drive up to Fairplay, Colorado, where the atmospheric pressure is lower and the temperature drops to 0 degrees Celsius. When you finish lunch, you check your tire pressure. What does the gauge read? Okay, good. So this is an idea of the ideal gas law, where you got pressure, volume, temperature, number of particles even. In this problem, we're assuming that the number of particles stays the same. The tire doesn't have a leak or anything like that. But we have temperature, pressure, and looks like that's all here actually. So we want to figure out what this final pressure is reading. Okay, all right, let's take a look at this one in more detail. Okay, so we start out at 10 degrees Celsius, which is 283 Kelvin, just add 273 to that. And we're going to a place where the temperature is lower. So the lower temperature is 0 degrees Celsius, which is 273 Kelvin. Now when we start off, well, first of all, let me review something here with you. Usually at sea level, atmospheric pressure is 101.3 kilopascals. We're at elevation. So we're at a place where we start out with the local atmospheric pressure being less than 1 atmosphere, something like 85% of it actually. So you start at 85 kilopascals. Oops, let me get rid of that K. Don't need the K there because I already got the times 10 to the third. That's the local atmospheric pressure. And now the gauge pressure in the tires we're starting off with is 210 kilopascals. So 210 times 10 to the third pascals. Okay, so the absolute pressure, you have to add those together. 85 plus 210 gives us 295. Where am I getting that from? From this formula here. So the gauge pressure is the absolute pressure minus atmospheric pressure. So if you take a tire gauge out and you measure, before you even measure your tires, it's reading nothing. It's already been calibrated to take into account atmospheric pressure. That's the way to think of your gauge. So like if you have a tire gauge in your car, just pull it out, it's reading nothing until you actually measure the pressure. Okay, so this is the way it works again. So the gauge pressure is the absolute pressure, and you're taking into account atmospheric pressure. So to get the absolute pressure, you take the gauge pressure and you add it to atmospheric pressure. That's why I added them together. Okay, so we start out at 283 Kelvin, and the pressure that we start off with is 295 times 10 to the third pascals. Okay, and then we're going to a location where the temperature is less, 273 Kelvin, and we want to know what is the pressure at this new location. Specifically, we want to know what's the gauge pressure. So we can figure out the absolute pressure using the ideal gas law, and then we'll have to subtract off the local atmospheric pressure at that location, which I think they tell us the local atmospheric pressure is something like 75. We'll have to take a look back at it in just a minute. Okay, so here's the ideal gas law. This is kind of the physics version of it. PV is equal to NKT. So here N is the number of particles. This is Boltzmann's constant. That's the temperature. Now if you've taken some chemistry, maybe you've seen it like this. PV is equal to little n, so the number of moles times the gas constant times the temperature. It's the same thing. We can convert from this formula to this formula by expressing the physics version in moles, and then there's a new constant involved. Okay, so what's not changing in this problem? The number of particles and the volume. We're assuming the volume is staying the same. The things that are changing are the pressure and the temperature. Okay, so you can rewrite these conditions like this. P1 over T1 is equal to P2 over T2. And what we're trying to figure out is P2. That'll give us the absolute P2 pressure. You'll have to subtract off again the local atmospheric pressure to get the gauge pressure. Okay, so we've got P1 over T1 is equal to P2 over T2. So we're solving for P2 then. So P1, T2 over T1. Okay, and then we have everything here. These are all spelled out for you here. Okay, so let's see. Let's put these in and see what we get. So P1 was 295 times 10 to the third. Adding both of those together from what we had before. times T2, so times 273 divided by 283. So I get for P2, let's see, 1, 2, 3, 4, 5. About 2.85 times 10 to the fifth. And that's pascals. That's the absolute pressure, 285 times 10 to the fifth pascals. They're actually asking for the gauge pressure. Okay, so the local pressure actually was 70% of sea level atmospheric pressure. So 70 times 10 to the third pascals. So we'll have to take this absolute pressure, subtract off local atmospheric pressure to get what the gauge pressure is. Okay, so if you take this minus this, you get 215 times 10 to the third. Depends on how you want to write it. Okay, so 215,000 pascals. Again, depends on what mode you have your calculator in. So by that I mean, do you have it in scientific notation or scientific mode, however you want to work on it. Anyway, this is the same thing as this. Okay, so how do we enter it into mastering physics? Let's take a look at that. Okay, so you probably have different numbers, but you can. This is how I'm just going to do it. 215,000. Now you've got to supply the units. These are pascals, so PA. Okay, good. It's always good to get the green arrow there. Okay. So this problem is a really good example of gauge pressure versus absolute pressure versus atmospheric pressure, and a little bit with the ideal gas law. Well, a lot, really. I mean, that's how we solve the problem. Okay, just two more to go here. So how much energy must be removed from a 150 gram block of ice to cool it from 0 to -40? The specific heat of ice is 2090 joules per kilogram Kelvin. Okay, so it's already ice. It's a 150 gram block of ice. And you want to take ice from 0 to -40. So there's no phase changes here. It's already ice. You just want to make it cooler. All right, let's look at this one. Okay, so we've got 150 grams. I'm going to call this big M because they call it big M in this chapter. Mass, 0.15 kilograms. The change in temperature is 40 degrees Celsius. Now remember, 1 Celsius corresponds to 1 Kelvin. So this would also be -40 Kelvin. So if you change it by 1 degrees Kelvin, you change it by 1 degree Celsius. Fahrenheit doesn't work out like that, remember, but Celsius and Kelvin does. The specific heat is 2090 joules per kilogram Kelvin. Here's the formula. The heat, MC delta T, we're trying to figure out the heat. That's how much is removed. Now really, just to be a little clearer, they could have said the absolute value of this, but they're saying how much is removed, so the magnitude. This will come out to be negative, but they just want the magnitude. Okay, so we got 0.15 kilograms, and then 2090 joules per kilogram Kelvin, and then the change in temperature. Again, we just want the magnitude, so I'm just going to write 40 here. I mean, you could put negative now and then make it positive later, but I just did it this way. Okay, so we can put everything together here. Let's look at the units. Kilograms cancel out, Kelvin cancels out, so we'll end up in joules. So energy, heat, all measured in joules. Okay, so we've got 0.15, times 2090 times 40. Again, technically it should be -40, but I'm going to be taking the absolute value in a minute anyway, so I just neglected to write that. Okay, good. 12540 joules. That's the magnitude of the energy that's removed. Okay, so you put the value here, and then put the units here. So the units again are joules. All right, let's look at the final one. What minimum heat is needed to bring 250 grams of water at 40 degrees to boiling and then completely boil it away? And then the specific heat of water is here. The heat of vaporization is this. So there's a phase change. We're taking water at 40 degrees. We are raising it from 40 to 100, that's the boiling point of water. And then after that, we are going to be turning it from water into steam. So there's a phase change going on. So we've got two processes going on. The previous problem, it was already ice, we just cooled ice. Here you got to take water, take it up to 100 degrees Celsius, and then you've got to vaporize it. That's what the heat of vaporization is. Okay, so there's two different parts there. Raising it up to a temperature and then turning it into steam. All right, let's take a look at that. Okay, so the total heat, it's two steps, like I said. There's the first step where you are just raising it, the temperature from 40 to 100. That's the first step, so I'm just calling it Q1. And then there's the part where we actually are evaporating, the steam part. So once we raise it to 100, we have to figure out the heat of vaporization. That's this Q2 here. Okay, so what you see here is raising the temperature part, MC delta T, we worked with this one already today, and then plus M times the latent heat of vaporization. And it's different depending on what substance you have. In this problem, we're given the mass, we have the temperature change. Remember, we're going from 40 to 100, so the temperature change is 60. Here's the specific heat of water, and here's the heat of vaporization of water given in the problem too. So you have everything, you just have to put it together. So I'll leave it to you to do that, but you have everything. You have the mass, the specific heat, the change in temperature, again the mass, and the heat of vaporization. Okay, excellent. You'll have to enter the answer in joules, which is no problem. Again, I think they gave it to you in Celsius, but going from 40 to 100 in Celsius is 60 degrees Celsius. It's the same change if you look at the Kelvin scale. Okay, so put everything together. This comes out in joules. Be careful with the units and you'll see that. Okay, if you have any questions, just send me an email and I'll talk to you soon.